In this video, we are going to see about Miller indices and its importance. Miller indices form a notation system in crystallography for lattice planes in crystal lattice. Miller indices are used to specify direction and planes. In particular, a family of lattice planes of a given Bravais lattice is determined by three integers h, k and l. Now, let's see the important features of Miller indices. There are many important features of the scheme of the Miller indices. They are all equally spaced parallel planes have the same index number HKL. When a plane is parallel to any of the three coordinate axes, its intercept on that axis is a infinity, hence its Miller indices for that axis is 0. When the intercept of a plane on any axis is negative, a bar is put on the corresponding Miller index. Miller indices do not define a particular plane but a set of parallel planes. It is only the ratio of the indices which is of importance. Example, the plane 422 are the same as plane 211. A plane passing through the origin is defined in the terms of a parallel plane having non-zero intercepts. Now, let me see the procedure for finding Miller indices. Choose a system of three coordinate axes, preferable along crystallographic axis. Find the intercepts of the plane on the three coordinate axes. Let these be x bar, y bar, z bar along x, y and z axis respectively. Then express them in terms of the axial units or primitives. Let them be x bar is equal to PA, y bar is equal to QB and z bar is equal to RC. Next, take the numerical parameters of the plane. Example, P is to Q is to R. The numerical parameters must be in whole numbers. Find the ratio of the reciprocal 1 by P is to 1 by Q is to 1 by R. Convert these reciprocal into whole numbers by multiplying each with them LCM to get the smallest whole number. This gives the Miller indices HKL of the plane. These are the explanation for important features of Miller indices and procedure for finding Miller indices. Thank you.
In this video, we will discuss about lattice energy of Born-Haber cycle. The method of calculating lattice energy, that is Born-Haber cycle. Application and determination of lattice energy. Sodium in solid state, change in sodium in gaseous state. This process is sublimation because solid is converted to gas is denoted by S. Sodium atom in gaseous state will converted to sodium ions. Chlorine in molecule state, change in chlorine atom state. This process is dissociation because chlorine is converted in atom is denoted by T by 2. First we will see lattice energy. Lattice energy is defined as the energy released in the process when the constituent ions are placed in the respective positions in the crystal lattice, or this is the amount of energy which is spent to separate the solid ionic crystal into its constituent ion. An experimental check on the calculated values of the lattice energy may be obtained from Born-Haber cycle. Born-Haber cycle for NaCl is represented as follows. Here S is heat of sublimation, D is dissociation energy, I is ionization energy, E is electron affinity. The cycle can be explained as follows. Initially, we start with solid sodium and chlorine molecule. The solid sodium is subjected to the sublimation energy S and it is vaporized to the chlorine molecule. Dissociation energy D is supplied, and as a result it is dissociated into its constituent ions. Here T by 2 is a dissociation energy per chlorine atom. Next, ionization energy I is supplied. The outer electron of any gaseous atom is removed. This electron is added to the Cl atom. As the Cl atom has the electron affinity E, and energy E is given out. The two ions Na plus and Cl minus are arranged in the lattice, and hence the lattice energy U is released. We again reach the starting point by supplying an energy. Del H known as heat of dissociation. Now S plus D by 2 plus I minus E minus U plus del H equal to 0. U equal to X plus D by 2 minus E plus I plus del H. All quantities excepting U are experimentally determinable. Hence the lattice energy U can be calculated. Thank you.
I am K. Gayatri from 3rd BSc Physics, Dr. Umiyal Ramanathan College for Women, Karaikudi. My subject is Solid State Physics, Unit 3, Topic Free Electron Theory. In this video, we are going to study about the free electron theory of metals. Free electron theory of metals is to explain the structures and properties of solids to the electronic structures. This theory has been developed into three main stages. So the first is the classical free electron theory. Drude and Lorentz proposed this theory in 1900. According to this theory, the metals containing free electrons obey the laws of classical mechanics. The determinant of metals as containing a gas of electrons completely free to move within it. To describe the thermal properties of metals, later on mechanics became the basis of theory of most of the general properties of simple metals such as sodium with 1 free electron per atom, magnesium with 2 and aluminum with 3. The traditional metals such as iron have partially filled electronic. These states are not treated by the free electrons of metal. Valence electrons are involved in electrical conduction in metals and alloys. Valence electrons become free in solid and move about randomly within the solids in the same way molecules in a gas confined to a container. Hence, they are known as free electrons. Neglecting electron-electron interactions and electron-ion interaction, it is similar to situation that electrons undergo periodic collision with ions in the lattice. This was about free electron theory. Now let's see the quantum free electron theory. The quantum free electron theory is developed by Sommerfeld in 1928, applied the principles of quantum mechanics to a classical free electron theory. And next, assumptions. The energies of free electrons are quantized. The distribution of electrons is as per the Pauli's exclusion principle. Electrons travel under constant potential and confined to the boundaries of metal. All the attractive and repulsive forces are neglected. Electrons on this energy level are also called fermions or obey the Pauli's exclusion principle. The highest occupied energy level by the electron at 0K is called Fermi energy level. Each energy level can accommodate at most 2 electrons. At 0K energy levels, below the Fermi levels are completely filled, and above Fermi level, all the energy levels are empty. If the temperature increases above 0 Kelvin, the probability occupation of electrons at that level is half, and the particular energy of that levels is called Fermi energy. The value of Fermi energy in metals about 5 electron volt. Now let's see the definitions and some relations. The first one is drift velocity. The drift velocity is defined as the average velocity acquired by the free electrons of a metal in a particular direction by the application of electric field. And second one is relaxation time. It is defined as the time taken by the free electrons to reach its equilibrium position from the disturbed position in the presence of electric field. And next one is collision time. Collision time is defined as the average time taken by the free electrons between two successive collisions. And current density. Current density is defined as the magnitude of current passing through unit area. So when J equal to I by A, J is the current density, I is the current, A is the area. This equation is written as I equal to integration J into ds. Now let's see the expression for relaxation time tau r. When the metal is subjected to an external electric field, the electrons move opposite to the applied field. At the removal of electric field, the drift velocity decays exponentially as Vd equal to V naught exponential of minus tau divided by tau r, where V naught is the initial velocity of an electron before application of electric field and tau r is the relaxation time. If tau equal to tau r, then Vd equal to V naught exponential of minus 1 or Vd equal to V naught divided by E. Thus the relaxation time may be started as the time taken for the drift velocity to decay 1 by E of its original initial value. Now let's see the mean free path lambda. The free electrons in a metal are continuously moving in all directions and various speeds. They frequently collisions with one another. Therefore, they move in straight line, constant speed between two successive collisions. Therefore, the average distance traveled by the electron between two successive collisions is called mean free path, or the mean free path is the average distance traveled by an electron between two successive collisions with other free electrons. Therefore, lambda can be written as lambda equal to c bar tau, where c bar is the mean square velocity of electron, where c bar can be written as c bar equal to root of 3 kBt divided by m. Then kb is the Boltzmann constant and T is the temperature and m is the mass. Now let's see the success of free electron theory. This theory was successfully explains this Ohm's law. That is the electrical conductivity of metals. It explains the electrical conductivity sigma equal to n e nu, where n is the electron density, e is the charge on electron and mu is the mobility of electrons. And next they explain the thermal conductivity of metals. The thermal conductivity of metals is K equal to Kb Nv lambda divided by 2, where Kb is the Boltzmann constant. Next, the Weidmann-Franz law states that the ratio of thermal conductivity and the electrical conductivity of a metal is proportional to the temperature T. It can be shown that L equal to K by sigma T equal to 2.44 into 10 to the power of minus 8 W ohm per K squared. This number is also known as Lorentz number. And next, the several limitations of free electron theory. According to this theory, conductivity of metals is proportional to the electron concentration. If used to always to divalent, aluminum and zinc etc. This model cannot explain the classification of solids into conductors and semiconductors or insulators. The theoretical value of mean free path of electrons as calculated from this theory do not agree with experimental values. Theoretical value of specific heat and electronic specific heat as calculated from this theory do not agree with experimental values. This theory could not explain why metals have positive value of Hall coefficient. And last, the Weidmann-Franz law deviates at low temperature of limitation of free electron theory. Thank you.
In this video, we are going to see Hall effect. So what is Hall effect? When a magnetic field is applied perpendicular to a current carrying conductor,
a voltage is developed across a specimen in a direction perpendicular to both the current and the magnetic field. This phenomenon is called Hall effect. The voltage so developed is called Hall voltage. Hall voltage and Hall coefficient. Consider a slab of material subjected to an external electric field Ex along x-axis and a magnetic field Hz along z-axis. As a result of the electric field, a current density Jx will flow in a direction of Ex. Let the current be carried by an electron of charge minus E. The external magnetic field Hz applied perpendicular to a current will exert a transverse magnetic field deflecting force on an electron, which causes the electron to drift downward to the lower edge of the specimen. So there are three variables used here: electric field Ex along x-axis, magnetic field Hz along z-axis, current density Jx will flow in a direction of Ex, and an electron of charge minus E. So the next is the experimental determination of Hall coefficient. A thin metallic strip several millimeter wide and several centimeter long is placed in x direction, and a magnetic field B is applied in z direction. A suitable current is passed in the specimen, which can be adjusted by the rheostat. Two potential LEDs are placed between point A and point B, which are connected to a sensitive calibrated potentiometer to measure the developed Hall voltage VH. By measuring the Hall voltage, Hall coefficient can be calculated. So here is the experimental setup of Hall coefficient. The value of Hall electric field is given by EH is equal to minus JXB by NE. Let I be the current flowing through the specimen. Let B and D be respectively the breadth and the thickness of the specimen. The current density is given by Jx equal to I by B into D. So next, EYD equal to VH is equal to minus 1 by NEB into B equal to RH into IB by B. Hall coefficient RH is equal to VHB by IB. Thus, the value of Hall coefficient RH can be calculated by knowing I and B by measuring experimentally the Hall voltage VH developed across point A and point B by means of calibrated potentiometer. Application of Hall effect. It is used to determine whether the material is p-type or n-type semiconductor. If RH is negative, then the material will be n-type. If RH is positive, then the material will be p-type. Second one, it is used to find the carrier concentration, mobility of charge carriers mu E, mu H, and the sign of current carrying charges. It is used to design magnetic flux meters and multipliers on the basis of Hall voltage. Next, the last one is it is used to find the power flow in an electromagnetic wave. Thank you.
In this video, we are going to study about the high temperature superconductor. The superconductor can be used to number of applications due to zero resistance. In critical temperature of superconductor is very low temperature, need liquid helium is very costly. The high critical temperature was required. The high temperature superconductor is discovered by J. George Benson and K. Alex Muller in 1986. The critical temperature greater than 77 degree Kelvin. The superconductivity can be maintained with liquid nitrogen. In addition to the high critical temperature, is also exhibits the extreme type 2 behavior. The high Tc superconductor is divided into three groups. First, copper-based components. Second, iron-based components. Third, hydrogen sulfide. Copper-based components. Layered ceramic materials with planes of copper oxide. Bismuth, platinum, calcium, copper oxide, yttrium, barium, copper oxide, etc. Iron-based components. Iron-based components contains layers of ions and a bacterigen such as arsenic, phosphorus or collogens such as oxygens or sulfurs. LNFeAs, LiFeAs. Hydrogen sulfide. When the solid filled hydrogen sulfide, the compound contains the electricity without a resistance at 203.5 Kelvin. This is more example of high Tc superconductor. So all the materials are copper oxide and you can see the CuO4, CuO4, Cu3O7, Cu3O7, Cu3O. This is all the copper oxide are introduced. YBA2CU3O7 having 92 Kelvin, Tl2Ba2Ca2Cu3O7 having a 125 Kelvin, GH 0.2, TL 0.8, Ca2Ba2Cu3O having a 139 Kelvin. This critical temperature are greater than 77 Kelvin. This is called a high DC superconductor. There is the advantages of high DC superconductor. As critical temperature of HTS is more than 77 Kelvin, it can be easily maintained using the liquid nitrogen. The high DC superconductor exhibits extreme the type 2 behavior, that is the critical field is also very high, so HTS can carry very large current even in very strong magnetic field. If HTS are used in critical power distribution network, the network will be compact due to the high current carrying capacity. Because of reduced size and weight, can be used effectively in magnetic leviation application like MACLO. This is the important applications of high DC superconductor. HDS has application in scientific and industrial magnet, including in use MMR, nuclear magnetic resonance, and MRI, magnetic resonance imaging system. Commercial systems are now available in such category. The efficiency of system using HTS will be more. This is a disadvantage of high DC superconductors. The commercial applications for high superconductor have been limited as the currently known high DC superconductor or brittle ceramic, which is expensive to manufacture and not easy formed into the wires or other useful shapes. They cannot be used in electrical apparatus like transformers, generators, and motors very easily. This is the disadvantages of superconductor. Thank you.